Testing. 听到声音 OK. Okay. So check. Okay. So welcome everyone for this seminar. So my name is Jian, and today I would like to present quantum mechanics and also quantum field theory. In the specific area for quantum field theory is about standard model that I learned as much as I can. Then I will present you guys. If you guys have any questions, like which thing that you are I not presented well, or you are not clear for what I am saying, you can just interrupt me lah. Okay, you can just raise your hand and just interrupt me. Okay, so basically we want to start with something, right? We will start to ask what is that kind of words. So quantum mechanics. Okay, the idea of the quantum mechanics, if you divide it into two words, okay, the quantum and mechanics. So you try to look at the Chinese side, it's called 量子. And if you try to understand what is a 量子, and it's somehow is describing the discrete or quanta. And the meaning of that quanta and discrete is coming from an experiment that imposed by that done by some physicists, and there is a problem, and they want to quantize the energy. So it's kind of the new word, English word. In fact, there's a word in Latin. If you try to search quanta, is meaning of different things. But the idea of that in quantum mechanics is like you try to imagine that it is discrete. Like the mathematics, discrete mathematics is like 1, 2, 3. It's not continuous. Yeah. And for mechanics, we try to study of the motion interaction of physical objects. So we call it 力学. If you try to devise it, it becomes like 力, the study of the force, okay, that related to that metals. Okay. And this is my plan for these 2 months. So the introduction, I would like to try to present to you guys the motivation, some of the historical developments, okay? And we'll just briefly go through that. We try to, if you want me to be specific enough to touch on something, because it comes with the development of classical mechanics, thermodynamics, electromagnetism, then it leads to this kind of new field. Okay, so if you want me to specify on something, so I maybe need some time to prepare for that, and need some time to properly derive the formula. So most of the time I will just, for this specific for the first today, I'll just give you the idea and some of the formula that in fact we derive it. Okay. And the formalism, maybe you heard of that, is bracket notation. The notation that used in the quantum mechanics, and there are some formalism, mathematical formalism, and trying to apply in quantum mechanics. The operators, brackets notations, and when we're trying to formalize it, we have the mathematical tools already. So we want to apply in some potentials. Okay. For example, harmonic oscillator. That harmonic oscillator that you can think like the spring mass. Okay. That kind of the equation that related acceleration is proportional to negative x. Okay. So the harmonic oscillator, and some of the there will be the artificial potential, so which is not really in the experiment can do, and we will apply in hydrogen atom also. Hydrogen atom that the kind of potential. Okay, when we apply these small particles, microscopic levels, in different of potentials and try to describe using the quantum mechanics. Angular momentum, spin, etc. The idea of spin, which in fact coming from the Stern-Gerlach experiment, is describing that the particles have the intrinsic properties of spin. Why is that? We will see later on after some lectures, after some seminars, sorry. And identical particles that mostly in front of that we describing the one particle only. So identical particle in the sense that we have different particles. So how can we collectively describing them in a single equation in depth quantum mechanics? Scattering theory, I'm thinking on to add it because in quantum sorry in quantum field theory, mostly on the standard model, mostly dealing with the scattering theory. Okay, later we will see. Okay, so there are some quote that I heard of. If you think you understand quantum mechanics, you don't understand quantum mechanics. Is by famous physicist, and I can safely say that I understand, which implies that I don't understand quantum mechanics. So yeah, there's the idea that, but I don't quite like this idea because I believe that we can use the efforts is somehow to learn this subject, although it's quite counterintuitive. Counterintuitive in the sense that you cannot match with our macroscopic view. Macroscopic view is like you cannot see how this quantum mechanics behavior apply in this macroscopic view. Okay, these are some of the reference. Maybe I will use this. The first few part I will using the exactly is by the second one. Okay, the first one is the standard graduate quantum mechanics book. Yeah, we will try to use it in this seminar. So many will based on this few reference. Many will based on the first reference, and with others. One of the book that I like is the sixth one. The Chinese word is like 上帝掷骰子嘛. So I read it in my high school. So the kind of it's not a proper textbook, but it gives you the sense of what historical development that they are developed and what is the idea they developed from this experiment, etc. Okay, so it's like a general book, 科普书. Okay, and for the last two I'm trying to read it because it's more about the mathematics they are using. They more emphasize on mathematics in quantum theory. So, like for example, in the first one, the second one, they are emphasizing on the groups representation, how we can use this mathematical language to apply in quantum theory. Okay, so yeah. Everyone okay? Yeah. So I will start with some introduction. Okay. So when we're talking about quantum theory, quantum mechanics, oftentimes in my knowledge, I can see that they start with two ways. One is the historical development. They trying to start with that and give you the idea of why quantum mechanics so important nowadays. And the second one is start with the formalism. So I will start with the first way, telling you that why this all experiment leads to this quantum mechanics. Okay, so I'll start with introduction. So in that time, if you recall back to 19th century, like the end of the 19th century, the physicists are quite successful. They have the tools like classical mechanics, that's mainly on by Isaac Newton, like the three laws, Newton first law, second law, and third law is quite can explain most of the classical stuff. And also the second one is the classical electromagnetism. Electromagnetism, how the charge, how the magnet interact with each other. Okay, so it's around end of the physics. The classical physics are quite successful. Yes. Okay. The thing that I mentioned, classical mechanics by Isaac Newton and classical electromagnetism, and they are different with the modern electromagnetism, which is we call it as quantum electrodynamics. Okay, quantum electrodynamics, when we try to use the quantum field theory language to describe the electromagnetism. Okay, and the third one is the thermodynamics. The thermodynamics is kind of like if you're trying to use language that collectively describing the particles. Because let's say you have this room, right, have many particles. If I use the classical mechanics, for example, the classical mechanics, the Newton third law to describe every particles, and you have a plenty of equations, so you cannot solve it for all of them. So the thermodynamics, it kind of like study the group of collectively behavior of the particles that we can see it, for example, temperature, the pressure because of the particles that many particles like giving the force on a specific area. Okay, so this collectively nature, we try to use that language to describe. Okay, and it kind of successful that it's very successful that the people physicists think that the physics is done already. So why it's done already? So there's a kind of people. There's a people called Max Planck. Max Planck, okay, he want to study he want to study physics, okay, and his professor tell him the physics is quite successful, so you no need to come physics again. Yeah, but Planck, Max Planck respond to his professor, so his response is quite interesting. So I don't want to discover anything, just learn the fundamentals. Okay, so in fact, Max Planck is one of the founders of the quantum mechanics. Okay, it's that kind of successful that we can explain most of the physics and why we want the quantum mechanics. But classical physics, I use CP. It fails at some field. Sorry, it failed at some experiments. Okay, they see that it's like it exists some dark clouds in the physics. So they're trying to describe it using the tree of the language, but they fail to describe. Okay, so clouds. So when the physics at very high speed, okay, very high speed. So you can imagine that we using the Newton's law to describe the motion of us, how we can drive a car, how many speed, how many velocity. But when the speed is approaching to speed of light, it's comparable. Comparable in the sense that you cannot ignore it. There are some magnitude of order. Just if you compare the velocity of yourself with the speed of light, is it Like if you're dividing it, is it the magnitude of order, is it very, very small? For example, -6, like -5 or -6, we can ignore that. We can ignore that effect already. Okay, so when we want to apply the physics in the very high speeds, for example, the GPS that we are using, and also when you want to send a rocket, okay, send a rocket to another planet. Like for example, you want to send a rocket to Moon or Mars, they need that kind of mechanics to describe it, but it failed. Okay, variable to see. And another thing they fail at microscopic scales. The things are very, very small. Okay, microscopic. Microscopic scales. Okay. We will see how we describe what is a microscopic. Okay, in after some seminars, we will describe how this can be specified. What is a microscopic? What is our macroscopic? Okay, there are some of the experiments. For example, black body radiation. Black body radiation. They fail to use the thermodynamics and electromagnetism to describe an black object. It's an ideal object, ideal black object. They will totally absorb the electromagnetic wave and totally emit the electromagnetic wave. Okay, so if you have question, can just ask me. Okay, yeah, the black body radiation, they fail to describe it. And the photoelectric effect. And the second one is a photoelectric effect. Photoelectric. The experiment done by the Hertz. Okay, the Hertz, the frequency you are using the unit of Hertz, right? So they count is that paper, okay, done by Hertz when he is doing the experiment on radio wave. So he accidentally found that the photoelectric they are the effect that when you shine the electromagnetic wave, for example, the light, electromagnetic wave can compose of light, visible light, radio wave, X-ray, and etc. So in that situation, when he noticed that the X-ray is affecting the matter is trying to do the experiment. Okay, we will see the photoelectric effect in details later.
This is done by Einstein?
Yeah, it's done by Einstein to verify the experiment. But the first one to discover that is by Hertz.
What do you mean by this
one? Discover that is notice that effect. What Einstein did is a successful to explain the effect with the formula. I explain why this they have this effect. So yeah, the Hertz is noticing. It's like notice, oh, why this is happened, but he don't know. So later time, Einstein proved this with successfully explain why this will happen.
You write this in detail.
Yeah, let's see. And atomic stability. Atomic stability in the sense, if you study chemistry in high school, there are different models. It's like Rutherford models, Bohr models, and we have nowadays is the quantum mechanical models. Okay, we will see in details why the Rutherford model is failed. Okay. In one sentence is it failed because of electromagnetism that predicts the electron. Later we'll go through in details. And atomic spectroscopy. Atomic spectroscopy. Atomic spectroscopy. In the sense that, for example, you have the hot gas. Okay, hot gases. They're trying to shine hot gases. Hot gases. They're trying to shine the light. In physics, we are using light. Sometimes we're using light as electromagnetic wave. When we want to specify to the light that we can see, we are calling that visible light. Okay, 可见光. So sometimes we are using light to describe it as the EM wave, electromagnetic wave, which consists of like X-ray, radio wave, infrared, visible light, and so on. They shine a light on the hot gas. They are getting the spectrum. Okay, the spectrum is, they have a continuous spectrum, but they have a dark line. Okay. For example, if you're shining a visible light, you should be able to see 红到紫 red to violet, red to violet. So, but then there are some dark lines there. So, they cannot explain why this will happen. Okay, there will be some challenges. Those challenges that I fail to describe in it. Okay, and we'll see the developments of quantum mechanics. Okay, before the formalism, we are saying that the physics, the quantum physics, is all quantum physics, because they are doing like they are trying to use some of the equations like mathematics, like they impose a discrete energy, for example, in some mathematical equation, but they don't know why. Okay, is that kind of idea before the formalism? They don't have a systematic way to describe why I have a discrete energy in my thesis, for example, but they just do it because they can get the result and verify by the experiment. Okay, is that the idea we are calling that is all quantum physics. Okay, so before that, we'll see how it develops up. The first of idea of the discrete quanta, it comes from Planck. Okay, so in fact, Planck can let me see the time. Okay, in 1900, radiation. The introduction idea, the idea come up with quanta. Which leads him to get the Nobel Prize in 1918 and 1905, which is the photoelectric effect. Photoelectric solved by Einstein. Okay. And the idea of developed from that thesis is photon. Okay, it's another term that we don't know. Later we will see. Photon. Einstein. Okay, so 1913. Is Bohr atomic models. like Bohr. Okay. Bohr atomic model, um, it get the idea from the photoelectric effect, the idea of photon, the quanta, discrete, discrete energy. Okay, so the idea from this Bohr atomic model, it impose uh, others than discrete angular momentum. They have a discrete state of energy. Okay, discrete state of energy. Okay, so and one of the discovery is that if before that they have two kind of people on the line, on the two kind of people that have the views on the visible light. Okay, so the first people think that the first kind of people, first group of people think that the light is particle. Okay, the light is particle, have a particle properties. And the second group of people is the think that light is wave. Okay, so the particle and the wave, before the quantum theory, they already argue with that. These two kind of people. Okay, so the light must be one of these. Okay, in fact, in 1923, there is a postulate or yeah, hypothesis. I can say hypothesis. Like they're trying to say this light is have a wave particle duality. Okay, what wave particle duality? From you can see from the quantum. Let me write down first. 1923. Quantum scattering. Okay, it's by quantum. It verifies the particle aspect of the wave. The idea is that they are trying to use the photon. Okay, the photon. Just give you I mean, the photon is the discrete. The light. Okay, the photon. The photon is indivisible unit of light. Okay, how they verify is the photon that in this sorry, the light is a particle, is a photon in that experiment. The quantum scattering, in the sense that they shine the light, maybe it's a wave, maybe it's a photon. They try to do the experiment on an electron. Okay. Maybe it's a photon, maybe it's a wave. They're trying to shine it on an electron, which is stationary, it's not moving. So the idea is that when you're shining the wave on, when you're shining a light on the electron, it should do nothing. Okay. If it's the photon, it's great. If the light is a particle, if you collide with an electron and give the momentum to a stationary electron, and the electron will recoil from that. Okay, so this one will be the scatter photon. scattered electron. Okay, which is described by the wavelength. Is there any other? Or maybe I just the scatter photon. Okay, the theta angle. And shining a light, which we don't know is it a particle wave. It described by the, in fact, the experiment is verified by this formula. The delta wavelength. So in fact, they found that the wavelength of a light, it changes. Okay, it follows this formula. The hash is we define as the Planck constant, and mass of electron and the speed of light. And the theta is the scatter angle. So the idea is that in this experiment, they verify the particle properties of wave, which they are not sure is it the light, is it particle, is it a wave. Okay. So, but then if you think of the wave, right? If you think of electron as a wave, you can see from this interference pattern and shining the double slit. The shining a light on double slit, or you can just use two fingers pointing on the light. You can see there is a different dark lines there. Okay, so the interference pattern, which is only can be done if the light is wave. You cannot deny. It must be only particle. Light is only can be particle. The light only can be wave. Okay. So, the experiment is further verified, but light can be particle and can be wave. So, in fact, de Broglie,
What does the
sorry.
equation do? What does the equation say? So you shine a photon to an electron, and then electron get hit away, and then the angle is for photon or for electron?
Oh, it's photon.
So photon hit the other way. So you measure the angle.
Yeah. The delta lambda is the wavelength of the photon, wavelength of a light.
So the light hit the electron, and then the light change color.
Yes.
The change color.
Yeah.
So this color is measured by this formula.
Yeah. Because changing of color.
And then this formula proves that it has a wave property.
Sorry, particle properties of the wave.
This equation works for particles. Not wave.
No.
But
it's like
the lambda is wavelength.
Yeah. So
particle has wavelength.
It only the particle collecting. If you think like the wave collide to.
Recording in progress.
So yeah, these are particle scattering, the elastic collision, for the particle and particle to collide. They are developed using that kind of the basic idea to align at this formula.
No, my problem is particle and wavelength.
Particle have wavelength. It's after the idea of maybe I should have mentioned this. It's after the idea of they emphasize, sorry, they're using the de Broglie wavelength hypothesis, which is we as a matter, I mean the particle, right? The particle or we self, we can behave like a wave.
So how is it defined?
How is it defined? It's calling as a hypothesis, but
What's the statement?
statement. Me right. Oh, okay. We propose that all material particles, like us or the electron, the proton, okay, the atoms, particles behave like a dual wave particle behavior. Behavior. If the it's starting from the momentum of a photon, okay, from the Einstein relativistic formula, when you substitute, sorry, mc squared plus pc squared, when you want to describe a momentum of a photon, which is massless, okay, which is massless, don't have a mass, so you substitute m equal to 0. I should define c is the speed of light, e is the energy, okay, m is the mass of the particle, p is a momentum. Okay, so if you substitute m equal to 0, you'll get p equal to e over c. Okay, it's after mentioning it's after the sorry, wait, what you call the photoelectric effect. Okay, maybe I will jump back to it again. Okay, in fact, the energy of a photon is given by hash nu. Okay, is hash nu. The nu here is the frequency. Okay, and he proposed that we substitute this hash c hash nu or c, and when you are thinking of the speed, speed is a relation of frequency is times with the wavelength. Okay, frequency times wavelength. So is for the light is moving on speed of light. So the frequency here we are using nu. And the wavelength, maybe you just give it lambda. Okay, so substitute is a hash over lambda. It's kind of weird in the sense that when you think like the electron or our cell is a wave also. Okay, but
wait,
yeah.
does this apply to mass when mass is 0, right? So we are not mass 0.
Oh, it's kind of like yeah. Okay, the mass is the mass is 0 when you're trying to use a relativistic formula. Okay, this is a question. Okay. What I found, I just tell you what I found. Then the de Broglie using the deploy using the momentum of photon. Okay, momentum of photon, which is described by P equal to hash nu over C. And just apply and give the hypothesis. Okay, in the fact that I mentioned that they use this they use the theory, the all quantum theory, which is not supported by the mathematics, and which you can think of kind of weird. Yeah.
So are you like still stand on that we have wavelength?
In fact, we are, yeah, as
But I don't think you can use this argument.
okay,
This is
massless.
massless.
Okay, it's a good point.
Yeah.
Yeah.
Maybe you should find it out. I think I heard that idea before. I don't know where it comes from.
Okay. I just give you what I found lah. Okay. This the hypothesis, and they are doing the other experiment. For example, let me find stated somewhere. It's kind of weird, like when using the physics to how to say. This is my understanding of like they are trying to use the relativistic formula to apply to get the momentum of a photon, and why in fact it can generalize to the human, or the particle nature, and they are using hypothesis, and somehow it describes the nature. So yeah, we'll find out why it can be generalized.
Another thing is when you use C equals to lambda V, you already assume it's a wave, right? Otherwise, how you get the frequency?
Yeah, so I think they call it hypothesis. That's why hypothesis is like they propose something axiom that cannot be defined. I mean cannot be modified.
Okay, it's okay. I mean,
Yeah.
you make what axiom you want, but I mean this axiom implies that the particle is a wave. I mean the photon is a wave, right? What is it?
You mean the photon is photon? Because of wave particle duality, so they use that formula of wave for formula.
No, wait, okay. So just now, are you deciding whether photon is a particle or wave, or you already like declare that
it can be two nature when they're trying to use that.
But now all your description is just based on wave, right?
No, duality.
Where's the particle side? Where I see the particle in the scattering?
Where is the particle in the scattering?
Yeah.
You mean this one?
Yeah.
I didn't derive it, but maybe I can work it out also. They start with the elastic collision, which is two particles that can collide. It's nonsense if you use wave collide with wave, right?
I don't know what is nonsense.
So why is nonsense? Usually we are using the particle to collide with the particle.
So I mean, if wave collide, they won't.
The effect is described by others.
Wait, okay. So that scattering, so you.
Is by assuming
how you
that.
observe it?
Okay.
What did you observe?
We observe. They observe in the change of wavelength, and that.
Change of wavelength. But how you measure the angle?
By measuring. How I measure the angle?
Yeah. So the light go down.
Yeah. maybe it's on kind of the surface
So the light band,
bend.
the light band,
The light, maybe you can think of like the light will bend
band.
from a metal surface. Yes, it have a electron.
So electron, do you see as a light proton? Do
Electron
you see electron? How do you see electron? Electron is
is
particle.
particle with both.
Oh,
Mm.
wait, before that, so how do you observe electron?
Yeah.
It's a light, looks like a light.
Okay, electron.
Physically looks like a light.
Before that, we think that electron is a particle because you know that.
No, I don't want to think about electron. I want to see the
Ah.
electron now. How does
Um,
the electron in real life?
Electron in real life
It's also like a light.
is a
It's a ball.
is it a ball?
Have you seen electron before?
No.
Then how they observe this scattered electron?
How they observe this scattered electron? Okay.
Okay, light, I can imagine a light.
Hmm.
Like if you shine the light straight and then it bends, okay, I know.
Hmm.
What's that? I never see that.
Yeah, so that's
I mean, you never see, but you should like
why is it?
know like how to observe electron, right?
Hmm. Okay, maybe this I work it out on. Yeah. But the idea, I think they simplified the idea how they observe it and how specifically they can observe the electron and just give the diagram only.
Because otherwise you
Yeah.
don't really know what they are doing then. What you say is just planning theory, so you don't know what's going on. So if you want really like how to do a proper theory, you need to like go down the field. What's really happening?
Okay.
Yeah, maybe you cannot. I mean, you cannot do hands-on on electron, but at least now you got the ability to read maybe their paper, their lab work, right?
Yeah.
Yeah. So now you suggest there is a particle because
The light.
yeah, you can see particle because it collide like a particle.
Yes.
Because you can see it like this. Because if let's say you take two water wave and then mix them together, it also bends, right? Sometimes. It bends, right? You change direction also, right? If you
you change
wave.
superimposed together.
Yeah. I think they also like change direction, right?
You can see the light change. The formula they're describing it when they starting out with that is they assuming the light is the particle. So and why they list in that formula hash over NEC 1 minus cos theta. Yeah, I think that there's assumption of a particle. No, there's assumption of the wave is a particle. Sorry, the light is a particle.
Can you write that down in your
The description.
Yeah.
Can.
You write down like.
I try to derive. See?
I mean, you derive it, then you say which part you need to assume it is a particle.
Can. Okay.
So, okay, so now assuming particle, then reach this formula. How about the wave part?
The wave part of a light.
Yeah. Is it required in this derivation?
Is it required in this? This one I'm not so sure because you mentioned that there is a wavelength, right? I mean, there is a lambda. Yeah, so
not sure.
There is, it's
I
not
think
sure.
you need to ask yourself,
Hmm.
are you is a light as a particle, or are they it as a wave, and then only then that can derive this, or maybe just one is enough. I don't know.
Okay. Sure. I will look at it again. This one. Okay. Another the body wavelength, right? Just now I mentioned about the body wavelength. It proposes this idea when the body is seeing that the the light have the wave properties which can be both in the interference and also have the particle properties. Assuming that is a later I will come back with. This one they see the light have a particle properties. Okay, and also which we will see after that the photon. Okay, the photoelectric effect. The light, I mean the visible light, the light in general is a photon. It's discrete. Okay. Yeah, which leads to him to propose this hypothesis. Well, maybe this maybe this light, uh, not just light have this duality. All the metals, like us, like the microscopic object, have the wave property also. Okay, and it verified by another experiment. It's called German experiment. Okay. It describing. Wait, let me see. I didn't write it down here, but it describing the wave nature of electron. Okay. Should I include the details also? Wave. The idea is that it verify the wave nature of electron, which we think that the in previously the electron, the proton, the neutron, we think that the electron is orbiting around nucleus. So electron is electron must be a particle. But in that experiment, which I didn't state the details, the Davidson Journal experiment, it verified that electron have a wave nature. If I can recall back, is shining on the. Wait, let me think. They have a detector. They're trying to generate an electron, shooting an electron. So previously, they have an interference pattern when an electron, when a wave shines on a metal plate, they will be scattering. They will be scattered and have an interference pattern. And in the experiment, there is a German experiment. They are using electron, shooting one electron at a time. When they are shooting more enough, they find that there is an interference pattern there, which the interference pattern is coming from the wave properties.
What do you mean by shooting more?
Shooting more enough.
2 at once, 3 at once, 4 at once, 5 at once.
One at a time, one at a time. They discover that they have an interference pattern in the detector.
I mean, 1 at a time and then
One at a time.
straight away see.
Oh no, it's a metal plate. They're shooting the electron, and they have a detector. The detector can this one electron can measure the fluctuation of the current because electron when they have because why they have current because of electron is moving, right? So they're using that measurement method to measure the electron bounce off. Yeah. So they get the interference pattern through the maybe they get the values already. They plot the graph. For example, is
What's the axis of this graph?
where's the axis of this? Theta, because you rotate when you see from outside, is a detector shining on the plate, and so the detector can be rotated like this. So they are measuring the angle and also they are measuring the current from the bounce of electron, and they are plotting the graph.
So where's the angle? Where's the angle? You said the detector can, and where's the angle?
Detector here, it can be rotated with the angle. This is the center. It's a circle. Can be rotated at the angle.
Has 0 to 1, 360.
Maybe 0 to, I mean, it's certain angle negative, because when you starting from here, 180 you touch the shooter already. So it's negative 90 to 90 degree.
Also only half.
Yeah. I forgot the interference pattern, the graph, but the idea is that they are measuring through spinning the detector, and they're plotting the graph is indeed same with the uh, interference pattern, interference behavior.
So but we were shooting. Okay, wait.
Mm.
Continuously shooting.
Yeah, continuous shooting.
So if it's particle, what do you expect?
It just bounce off, won't fill out, like won't make out a pattern of like the
Or you mean there
interference
will be
pattern.
a zero? There will be a moment which is zero current. Right. If it's just bound on one direction. And
Yeah.
the other direction you won't measure it.
No, it's like when I think when we think of a particle collides it, I think I come up with a details first, and I let you know that.
Okay.
Yeah, I think. And the next one, let me charge my laptop. Okay, so the idea of that, they develop the hypothesis of de Broglie wavelength, which we need as a wave also. We call it matter wave, 物质波. Okay. If you come back to that formula, h over lambda, okay, yeah. And if you accept this formula, I'm going to hash over P. The P here is our linear momentum. Sorry, is our momentum. Okay. The particle momentum. Okay. When you're trying to substitute the formula, maybe we are moving in 40 meter per second. Okay. You substitute into this formula. This one momentum is described by mass times the speed. Okay, because it's a magnitude only. So what is our wavelength? Okay, so hash here is indeed is very, very small, and maybe I should specify the Planck constant. Is maybe call 6.63. Maybe call let me check again.
Does it matter?
No. Okay. So the matter thing is that the magnitude order of magnitude of the value is very, very small. Okay, we will divide by MV here. Okay, so you will get a very, very small wavelength. So in why we cannot observe our matter wave. Okay. Yeah. So and after that, they come with the formulation. They're starting to formalize the quantum physics. Okay, there are two ways of describing quantum mechanics. First is through matrix mechanics. They are calling it as matrix mechanics. Right at here, it's around 1925. Formulation wave mechanics by Heisenberg. Okay. So basically, it's like eigenvalue problem, the diagonalization. They are trying to use matrix to describe the quantum mechanics. Okay, so they are quite successful in describing the discrete quanta of the light. Okay, and after that, they have the second formulation, which done by a different people. They have other way to describe the quantum physics. It's called quantum mechanics. And maybe you heard of that is by Schrödinger, the famous Schrödinger equation, or the Schrödinger cat.
Heisenberg is matrix.
Oops, sorry. Balik. Yeah. Matrix mechanics, wave mechanics. Yeah. In describing the state of a particle, it's a wave function. Okay, which we'll see after that. And indeed, it's a generalization of the Pauli hypothesis. Okay, they have an equation. Schrödinger, in fact, Schrödinger trying to Schrödinger come up with this equation, but he cannot explain why it should be use this language to describe the nature of a microscopic world. Then after after 1 year, something like that, they're trying to mass bond, trying to interpret it as a statistical interpretation. Of wave mechanics. Statistical interpretation, we should come back again, and they have a systematic way using the formalism, and they have two formalism, two formulation, and indeed they find that these two formulation in these are the same. Okay, in these are the same, and yeah, the wave mechanics and the matrix mechanics, they are described as same things. They can be described as same things. Okay. So the approach after the Dirac using bracket notation, and the representation of Dirac, the representation of quantum mechanics formalism in continuous basis. You have an idea of continuous basis and also the discrete basis. Indeed, continuous basis is wave mechanics, and discrete basis is the matrix mechanics. Okay, so this vector is lived in a Hilbert space. Okay. If you guys have any questions, you just watch the formulation. Bracket notation operator. Yeah, and after that is they have a systematic way to describe the quantum mechanics idea, and they are trying to physics is like this. We have this just now is classical physics, classical mechanics, electromagnetism, classical mechanics, electromagnetism, thermodynamics, and now we have a quantum mechanics. And just now you have a first cloud, right? First cloud in this is solved by relativity by Einstein. Yes, here the first cloud, first black cloud. So the classical physics fell at a very high speed. It is solved by the relativity. So we have 1, 2, 3, 4, 5. These 5 different fields already. So they want to govern it into a single theory. So
What's the 5 field? What are the 5 field?
Classical mechanics, thermodynamics, electromagnetism, relativity, and quantum mechanics. Yeah, the 5 here. So one of the approach they are trying to govern the relativity with quantum mechanics. Okay, so which leads to previously they called it relativistic quantum mechanics. After that, they found that they cannot use they have to use the fundamental they have to describe the things as a field. Okay, which is quite abstract. Thing like the particle there, the electron, we are trying to divide it. The electron is very, very small already. So they try to divide it into, maybe they have another fundamental particles, they think like that. And in fact, they found that there is a theory, quantum field theory, which is quite well explained the phenomena. Yeah. So which leads to there's another approach. Sorry, the approach is that they develop a equation called Dirac equation, which using the special relativity governs with the quantum mechanics. And this is successful predict the antiparticles. Okay. Yeah. Is enough for the history development stuff. Should I go to the second part or second part of the lecture? Okay. Other video. I actually have many things want to say. So, okay, we move to second part. Here. Wait a minute. Okay, so the second part of the lecture is second part of the seminar is quantum field theory, and the area which I wish to touch on it is the standard model. So I will start with the root, why standard model, how to get a standard model. Okay, and yeah, basically we say that the quantum field theory QFT, okay, is indeed need some working on quantum mechanics, special relativity, quantum mechanics, special relativity, and one more because it's a field, and they have one more theory that need to be added on is a classical field theory. Okay.
Recording in progress.
Okay. The introduction. What is the standard model? And I wish to cover some mathematics, which I'm trying to work on also. Maybe the different idea that I not quite understand, which I currently work on is contravalent vector, covariant vector. Yeah, I'm trying on working on that. So, and also the Klein Gordon. Maybe I try to write down here. Go to white center model, Klein Gordon equation. The mathematics preliminaries, Klein Gordon equation. It involves with the idea of spin. Okay, the spin that is scalar. Okay, so the idea I have still exploring on that. They have an idea of the scalar field, scalar quantum field, which is they are using Klein-Gordon equation to do so, and also the Dirac equation. Okay, which obviously more complicated equation. Yeah, and trying to risk up on Higgs boson, calling it as a God particle. Why is it so? The Higgs boson and mechanism. And the idea is of the Higgs mechanism. When we say that everything can be described by the quantum field, okay, the fundamental nature is not a particle anymore. So they are using the quantum field to describe our nature. One of the development that leads is they discovered the Higgs boson in 2012. Okay, after the standard model. So after the prediction of standard model. So standard model is a theory, and later we'll see. And it kind of gives the idea of Higgs boson give the masses to every particles, every matters. Okay, so this one I trying to work on also, like how they can lead to that idea. Yeah, so and finally it's a standard model which we will see in more details. they have the weak force, the weak force, the strong force, okay, and also the different kind of particles. For example, boson and fermion. Boson, okay, where? Okay, so we'll see the standard model. Okay, so we start with what I understand is they start with two stuff. Um, okay, the boson or the gas boson. This is my plain understanding. I don't understand why they have um, have this thing. The plain understanding is like the gas boson. They have a labile boson. The gas boson, I think the gas is something that come from gas symmetry. Okay, so which is I currently trying to understand. And the gluon, the photon. Okay, the boson have the integer spin. We didn't introduce the spin, but just give an idea the integer spin. Okay, the integer spin, and we can call it as the force particles. Okay, why the force particle? This four thing, the force particle gauge boson, and it's not following Pauli exclusion principle. Pauli exclusion principle. The Pauli exclusion principle, which many only apply to fermions. Which the fermion you can there is only four fundamental fermion. Okay, 1, 2, 3, 4. The four fundamental fermion, and like one here. First one is electron. The second one is electron neutrino. The up quark and the down quark. Okay, they have these four fundamental fermions. And what is the other part? Other part, they just made the two copies. And why two copies? Yeah, still in discovery on that. Two more copies of each of it. Okay, for example, electron. The another two copy is muon and tau. Muon and tau. Okay, they kind of like run out of the name. This one is calling the two copies of this electron neutrino. The other name is muon neutrino. Okay, you can see a muon here. The left side muon and right side muon neutrino, and this one you can guess is yeah, tau neutrino. Tau neutrino. Maybe I try to write down. This is the electron. Okay. Neutrino. Okay, so the up quark, down quark, okay, the two fundamental fermion particles. So we make another two copies. Okay, for up quark is charm and top. CHARN, quark, charm quark, and top quark. And for the down quark, they have a two copies. So it's a strength quark, strength, and the bottom quark. Okay. So this one is the whole standard model, and one more is a Higgs boson, the God particle. Okay, they have a spin 0. Higgs boson. Okay, you can see that the boson is described by this integer of spin. Okay, so for example, the Higgs boson is a spin 0, and the outside of it, here, the photon, gluon, W boson, and Z boson is spin 1. And the outside is, we are calling it as the fermions. Maybe I just highlight it with the red color here. We are calling it as the fermions, which is following the Pauli exclusion principle. And you can think the Pauli exclusion principle can be applied to electrons. You heard of that maybe? It's actually because of its fermion, and why it follows the exclusion principle. I will try to find out. And there are something that still in discovery, because this one is quantum field theory is governing the quantum mechanics with the special relativity.
What's the spin of fermion?
Spin of the fermion is a half integer spin. So for example,
Half integer spin, understand? Yeah, very good.
Okay.
Integer, right?
Half integer.
Yeah. 1/2 2.
Yeah. 1/2.
2. 1 also count as 1/2. So you can get half 1 written 2.
1/2 3. 1/2, 3/2.
And then 2. Can 1 be 5/2?
Or the 5/2, 3/2, 5/2, 7/2. Like this whole integer is for boson. Yeah. For example, I have specified. Fermions. Okay. Because these are the fundamental particles we are talking about. It can be all the metals can be described by this diagram, standard model fundamental particles. So the fermion outside of it, the outside specifically all are spin half. Okay, all are spin half. Why I say fermion can be applied to 3/2, 5/2 when you collectively composite it. Okay, just an example, the quarks, maybe it can be 3 quarks form 1 proton. But if you subdivide the proton, it can be 3 quarks. Okay, so the proton is fermion because total spin is 3/2. Because of 3 times 1/2. Yeah. So the kind of idea can be like composite particles, proton, neutron. So yeah, thing that I want to mention, they are trying to find the graviton because they want to governing the gravity inside this standard model. So it's still in just it's outside. Okay, the graviton. It's a spin tube. They just a theoretical prediction, and that is one of the ways they want to govern this all physics. So one of the proposal is the graviton. Okay, and also another interesting things that the standard model cannot explain is dark matter, dark energy. Okay, because it is a dark in the sense that we cannot observe it. Okay, we cannot use the instrument to interact with it, so we cannot detect it. But theoretically, it exists at that. Okay, so dark matter and
Have you seen the recent news that they say dark energy is increasing?
yeah, dark. I saw one of the new is like, and this one I not here is decreasing.
I think you can have a look.
Okay.
Yeah, I also just saw.
Ah,
I don't know what it is. Seems like some folder is yeah.
Okay. So okay, so these are the just an introduction of the standard model. So yeah, this is why I learned from him. I'm trying to working on about the how the force it exists. Okay, they call the boson as a force particle. Why this scattering theory is important when two fermions, the two fermions exchanging the boson particles, fermion particle exchanging the fermion particles, and the gluon, photon, maybe boson and Z boson is is giving the force. For example, electromagnetic force, um, weak, weak nuclear force, strong energy force, a strong nuclear force. Yeah, this boson that dealing with that. Yeah, is how we can think of why the force is exist. Yeah, because they are changing the particles. I think this my it's my introduction for this second part. Okay, question.
So can you update whatever you say to the docs?
Can.
And then maybe you send me next week.
Okay.
So whatever you say will be completing the docs, right? Yeah. So try to what you say.
Sure. I try to complete the next part next week. The seminar, the one that I want to cover.
Also, I mean, no. That one can lead to later. I mean, I want you to like complete what you said.
Okay.
Those you can leave for yourself. Okay. Yeah, but what I want is whatever you say here, document it.
Okay.
Yeah. And then with the question that I gave to you, you fill it in. And then you give me before the next week.
Okay.
So that I can go through if I have any question, then I can ask and then you give it.
Okay. Sure.
So the level I want you to write is like a survey article on archive. Have you like any survey article?
Not so much.
Yeah, so I mean, you can try search a survey article on quantum mechanics or standard model, and then you will find a lot.
Okay. The seminar will be so the next week seminar. Does I need to mention again the question? Okay. question that bring out today.
Yeah.
Okay.
Because why I have a question? Because you're not clear. So you need to make yourself clear first. Otherwise, what you say not continue because whatever happens based on
What?
that problem.
Yeah. Okay.
So there's a logic for it. Otherwise, the logic cannot flow.
Okay. Yeah. Yes.
Okay, that's all.
Thank you. Thank you.
So my FYP is meeting tomorrow. Not Friday.
Yeah, will come.
Yeah.
Is A for I have a venue.
Yeah. Start from 9 tomorrow. And then we'll go for lunch about 12 and or before 12. Then continue again 1 o'clock.
Yeah, Richard.
Okay. Okay, thank you.
OK，好走神。中文你有课？我知道，而且1点到8点有课。
大可为正确放弃。